Hi, welcome back to My Smart Learning. It's been a while. I haven't seen you guys for, it's been 2 weeks over the Easter holidays. Hope you've had an okay holiday, bearing the circumstances. And I hope you're raring to go for your next lesson. This is a lesson designed for Year 10s. For my Year 10 class, we're looking at electricity in the home. So it's the physics lesson for my Year 10s, but it can be used for Year 10s, Year 11s for the GCSE Science and Physics lessons. So we're looking at electricity in your home. The main objective is what we're looking at is how does electricity get to my house? So how does electricity get to your house? Before we go on to that, remember we have our recall quiz. It's been a while, so if you've forgotten, high five. You get all 5 questions right, you get a virtual high five from me. Now, question 1 then. Write these down, have a quick go, pause it at the end of the 5 questions, just double check them, and then we'll go through the answers. Quick recall PT then. Q equals what? So Q stands for charge, measured in coulombs. What is the formula for it? How do you calculate it? Question 2. V equals, so the voltage or the potential difference equals something. E equals, so the energy, okay, energy is equal to what? Based on our electricity topic that we've done so far, because energy, there's lots of different equations for energy. However, the one I'm looking for is to do electrical circuits. The total resistance in a series, so if you remember back to our last lesson, the last thing we finished off on was our series circuits and our parallel circuits. So how do you work out the total resistance in a series circuit? And the last question, what are the rules for your voltage and your current in a series circuit and a parallel circuit? If you press pause now, check all your answers, give yourselves a few seconds to just do those questions and then just check them. So if you've had a go, the answers then, Q equals IT, quit. That's how you remember it, quit. Q equals IT. The charge is equal to the current times time. Voltage, V equals IR, based on Ohm's law. If you remember, Ohm's law is the current is directly proportional to the voltage applied as long as the temperature remains constant in my wire, in my circuit. So V equals IR, current times resistance. And E equals, the energy in electrical circuit equals QV. So it's the charge times the voltage, or the potential difference, which is the same thing. Now the total resistance in a circuit, the way you work out the total resistance, you just add up all your resistors. So if you've got a 5 ohm and a 5 ohm resistor in series, you just add them together. So 5 plus 5 would be 10 ohms. So you just add them up. So the total resistance in series is R1 plus R2. That's the way we tend to write them. And the rules then for your voltage and your current in a series and parallel circuit. Let's just look at the series circuit. The voltage or the potential difference in a series circuit is shared between the components. So if you've got 10 volts on your cell or your battery and you've got 2 components, let's say 2 bulbs, and they're exactly the same resistance, then your 10 volts will be shared between the 2 bulbs. You have 5 volts and 5 volts. The current, however, okay, remains the same at any given point around that series circuit. It's always the same at every point. In a parallel circuit though, your voltage is the same at every branch. So if you've got 10 volts in your cell or your battery, then the next branch will also have 10, the next branch will also have 10. No matter how many branches, they'll always have 10 volts. The current, however, remember, it splits at the branches. So as you go through one branch, some of the current will go through one branch and some will go through the other. So if you've got your, let's say your 4 amps from your circuit leaving your cell, as it goes through, if you've got the same resistance in each branch, you'll get 2 amps going through one and 2 amps going through the other, and they'll eventually meet up again and you'll get 4 amps again. So that's a quick review, a quick reminder of the things that we learnt about over 2 weeks ago now. And hopefully you remember them. So if you got all 5 right, excellent, well done. You get a virtual high five from me. Now, quick little thing to think about. I play this game in lessons sometimes. It's where you sort of play a tennis game with working out the number of electrical appliances you got in your house. So like one person might say TV, the other person you play it in pairs, the other person might say radio, the next person might say PlayStation, and so on and so on. And you keep doing that back and forth until one person either pauses or stutters or repeats the same answer, and then that person loses a point, the other person wins a point, like a bit like tennis. So a quick little thing for you to do, a little starter activity. If you press pause, write down a list of as many things as you can think of that uses electricity in your home. Okay, so think about it. So you might think, oh, I can only think of a few things, but actually, if you give yourself a good couple of minutes or so, you'll probably end up with a list of, 20, 30, 40 appliances, maybe even more, around your house, that you realize that actually we are very, very energy dependent. We need a lot of electricity in our homes. Okay, so press pause, write down a list, okay, and then I'll just randomly say some things out and then see if you got those on your list. Okay, so press pause, write a list. Okay, so if you've unpaused the video now and you've got your list in front of you, okay, compare my list to your list. All right, so on your list, have you got TV? You've got the TV there. Have you got TV on your list? Have you got laptop or a PC on your list? Have you got your mobile phone? Your mobile phone with the charger, because that gets charged. What about the lights? The lights in your home. Have you got that? Okay, so that should be general things. What about a stereo system for your music? How about your PlayStation, your Xbox? What about your iPad? What about your Wi-Fi router? Have you thought about that? How about, we haven't done our joke for the day, how about Alexa? Alexa, you want to tell us a joke?
Knock knock.
Who's there?
Aria. Aria who?
Aria who?
Aria going to let me in? It's freezing outside.
Aria, are you going to let me in? It's freezing outside. Well done. Anyway, so there's loads of things. If you go into your kitchen, think about it. You've got your microwave, you've got if you've got dishwasher, you've got your toaster, your kettle, you might have a food mixer, you might have a blender, you might have the fridge, you've got the freezer, you might have a washing machine, you might have a dryer, so, you might have all sorts of things. So you've got so many things at home that need electrical energy. And the list is, there's even more things. I can carry on with your list, hair dryer, hair curlers, electric heaters in the home, so on and so on. So many things in our homes. And so where does this electricity actually come from? How does it get to our homes? Well, it needs to come for either your renewables or non-renewable resources. Now, this is actually back in chapter 3 in the physics textbook, but it's a good reminder looking back at a previous chapter, because we're looking at the electrical circuits chapter, but this relates with that one. So it's across the syllabus. So what happens in your power station? It's our main way of getting electricity to your homes. You've obviously got your wind turbines, your solar cells, other types of renewable energy like hydroelectric and so on. But the vast majority of electricity comes through our homes through power stations. Two major types of power stations. You've got ones that burn fossil fuels and ones that generate that heat using a nuclear reactor. The nuclear fuel will generate heat. Now, with the normal, the vast majority of our power is produced by fossil fuels, so burning fossil fuels. So your fossil fuel could be coal, oil, or natural gas. As you burn that fossil fuel, it generates heat. Now, obviously, the byproducts of that, carbon dioxide and water, leads to pollution and things, and also climate change and global warming, because of the extra carbon dioxide warms up our atmosphere, and therefore we get ice caps melting and so on and so on. But we're not focusing on that area because that's a huge area of the topic. We're just focusing on how the electricity is being generated. So if you can see, you've got the boiler down there. Now in the boiler, I need to heat that water up to turn it to steam. So how can I do that? I can burn a fossil fuel. So if I burn the fossil fuel, it's going to generate heat. And that heat will turn that water into steam. And that steam then has only got one way to go. It can go through this little pipe here, and it will produce a very powerful jet of steam. And that steam, if you make it go through a very small nozzle, will come into this turbine area here, where it's going to spin these turbines. So these turbines are just metal blades. Imagine on an aeroplane, you've got the jet, and if you look at the jet in front of you, you see those metal fan, it's like blades. It's exactly the same as that. So you've got these turbines, and what happens is as the steam goes through that little hole, the turbines spin really fast, and that turbine is attached to a drive shaft there. That drive shaft is connected to the generator, and it causes the generator to spin. And the generator, as it's spinning, produces the electrical current. It produces a massive voltage, and it goes into what we call our national grid. So that's producing electricity, enters the national grid, and then that comes to your house to produce electrical energy for your kettle, so you can have a cup of tea or a cup of coffee, depending on what your tastes are. So what's happening in the generator though? The generator, you do go into this a lot more detail in a later topic in the physics, but ultimately it's not some mystical magic thing. In a generator, all you've got is magnets and a wire. And all you need is three things. You need magnets, you need wires, and you need movement. And the whole purpose of burning the fuel to make the steam to turn the turbine, it's for that movement, for that motion. Because I could go there with a bike and start pedaling and spinning that. And obviously I can't, because that generator is huge. It's probably the size of a double-decker bus. But the idea is if I got this to spin, just like on a dynamo, it'll generate the electricity. So I just need that movement. So you need three things. You need movement, you need a magnet, and you need some wires. And that's what's in the generator. You just got wires and a magnet. The magnet is spinning around in those coils of wire, and it's inducing a current, and you're getting electricity in those wires that ends up in the national grid, and then eventually to your homes. So that's it. That's how the electricity is generated. But what happens to that steam? You can end up just losing all that steam, and that'd be such a waste of that water. So what you've got is these things called cooling towers. And if you notice outside of the top of the cooling towers, you've got these puffs of white smoke coming up there. That's not smoke. That's actually water vapor going out and condensing, looking like little clouds. It's not pollution, it's just water. What's happening, if you stand underneath the cooling tower, it'll literally be raining on top of you, because what's happening is a lot of that steam is rising up those cooling towers, cooling down, it's condensing and falling back down, and you're recycling that water and using it over and over and over again. But some of the water you can't capture, so that's what's happening. Some of it's actually evaporating into the atmosphere. Now, why do we find a lot of power stations near a river? Well, it's a bit obvious. The river has water, and if that water will eventually run out because some of it's evaporating off, so we've got a source of water, we can just get it straight to that boiler. So that's your cooling towers. Now they do produce waste gases, but that actually comes from the boiler. There'll be a separate chimney for that boiler that doesn't look like the cooling towers. It'll look more like a long cylindrical tube coming out, made from bricks or concrete, whatever you, and you'll see smoke spewing out of that. That's the bit that's causing the pollution, not those two guys. So next time you're driving past one of those, maybe in your parents' car on the motorway and you see one of those, it's a bit of a misconception. People think it's pollution. It's not. It's water vapor, because they're called cooling towers. So that's your power station. Now once it comes out of your power station, so here's our power station there, it goes into something called a transformer. Now I'm not talking about those transformers, robots in disguise, not that type of transformers, you know, Optimus Prime or all those lot. These transformers, you've got them all around your house. You've got them on your mobile phone charger. I can go and pick one up from there, but then I'll disconnect everything. So what it does is your transformer either steps up the voltage or it reduces the voltage. Okay, because my phone doesn't require massive, thousands and thousands of volts. If I put thousands of volts through my TV or my laptop or my phone, it'll blow them up. Okay, they'll literally catch on fire and burn the house down, or you can get electrocuted. So what happens is you can these transformers will in your house reduce the voltage, but at the power station actually increase it. So you got the power station, and we'll start from here. So here's your power station. Now your power station produces approximately 20,000 volts of electrical energy. Okay, and a typical power station, that's 500 megawatts of power that you can generate. Okay, Now the problem with that is, you might think, wow, that's 20,000 volts, that's loads, I can use that. The problem is this though, if I get my power, because P equals IV, we haven't actually done that formula, but if I get my power is current times voltage. If I rearrange that formula, the current is power divided by the voltage. Now if I get 20,000, my 500 million watts, divided by 20,000 volts, I actually end up with 20,000 amps. Now that's a huge amount of current. And that current going through these wires, now remember, if you got current going through a wire, the wire gets hot. Because ohmic conductors, remember, we don't want, as a wire, too much current goes through it, the wire gets very, very warm and very hot. Now if you've got lots of heat going through those wires, you get energy losses, and you don't want that. You lose all that electrical energy that you're producing in the power station. By the time it gets to your house, it's all been dissipated, it's all wasted. So you don't want that to happen. So what we've got is a step-up transformer. This step-up transformer massively whacks up the voltage, and by massively whacking up the voltage, you're reducing the current, because they are, you can see they're inversely proportional. So if I increase this, I decrease that. So if I decrease that, what's happening is I massively whack up the voltage, I will have less current going through these wires, so I'll have less heating effect in my pylons, and therefore I'll have less energy losses. And when I get back to my city, I want to reduce the I want to increase the current and reduce the voltage, so it will blow my house, okay, or my factories. So in the first instance, you got step-up transformer. The step-up transformer goes from 20,000 volts and it whacks it up to 400,000 volts. Okay, so multiplied it up. I've multiplied and I've stepped up the voltage massively, so I have a step-up transformer. So reduce my current, got massive voltage. I go through the power lines across the countryside. So it goes through there. So I've got my 400,000 volts going through there. Because of the, you want to use the right types of materials as well, so you don't have much energy losses. But once it gets to my city, I'm going to step it back down. So I'm going to reduce the voltage now from 400,000 to 33,000 volts. So that's been stepped down. And then 33,000 volts you can use in huge places like massive factories or hospitals, and big industrial places where they'll use a lot of energy coming into them. Now they can have their substations within them, so they can lower it down as much as they want it for different parts of the business. But ultimately, when it comes to your house though, so you'll have a substation near your house, somewhere in your neighbourhood, and that substation will knock it back down. You have 33,000 there, it'll come back down to 230 volts, and that's what's coming into your house. So what's coming through my sockets and in your sockets throughout your house is 230 volts of electrical energy. Now it used to be, a long time ago when I was at school, when I was a wee lad, which is a long time ago, it used to be 240 volts, and sometime during when I was at school, when I've been teaching you, the government's decided to knock it down to 230 volts, so you got less energy wasted. So that's how you get the electrical energy to your homes. So you get your power station, it gets it to a step-up transformer, then you've got this thing called a national grid, which is a grid of these wires that go all around the country, and all the different power stations serve their energy into this national grid, so we can get energy from any part of the country to any part of the other part of the country. And then we've got these little substations and these transformers that bring the voltage down for our factories and our homes. So we've got a 230 volts there. What's inside a transformer? Now, a transformer, not a robot in disguise, inside you've just got an iron core, and you've got the same thing inside your mobile phone charger and your laptop charger. I've actually got my in my laptop, not disappearing anywhere, my laptop here has this little box. So this is the cable going into the plug, into the socket, and then this is connected to this box here, and then this is connected to my laptop, which you're looking at on the screen. This box is a transformer, that's why they're quite heavy. Okay, so in this transformer, I've got that. So you've got an iron core running through here. Now this one is a step down transformer, because yeah, that's a step down transformer. How can I tell? Because this is where the electricity is coming in, and this is where the electricity is coming out. So this is my primary coil and this is my secondary coil. Now you're going to learn the maths of this in more detail when you go to a later lesson further down in the physics, especially for the higher paper. But it's useful to know now that in my transformer I've got this iron core, so this is my iron core here. You have a primary coil, so I have a primary coil on this side because the electricity is coming through this wire from this wire here, that's 230 volts here, that's coming onto this side, and then I've got a coil on this side. So my primary coil is on this side and my secondary coil is on this side around this iron core. So this is a iron core. And in my primary coil here I've got more wires than I've got here, more turns in my coil there. So this is a step down transformer. If it was the other way around, if I had less this side and more this side, that would be a step up transformer. And a step up transformer is what you got at the power station side. So on the power station side you'd have less coils there and more coils there, and then electricity there would end up in the national grid, into the pylons. And then when it gets to substations, it goes like this. So substations will be like this, where you've got more coils on this side and less coils on that side, less turns of the coil on that side. And how does it work? Well, it's really weird, but what happens is you get an electric current coming through these coil of wire, it induces an electric current on the other side, which is a bit strange, but that's what it does. But what it also does is it splits it into ratio. So if you imagine I've got 20 turns there and I've got 10 turns there, that's half the amount of turns that are on that side. So if I've got 20,000 volts on this side and I've got half the turns on this side, I'll get half the electrical energy on this side. So if I had 20,000 volts there, I'll end up with 10,000 volts there because it's done in ratio, in proportion. Okay. So for instance, here is my transformer for my power pack for my laptop, and I'm trying to look on the back of this. It's 19 volts. The output's 19 volts. So let's just approximate it. So let's approximate it to 23 volts. This is a little bit more than this one. Okay, so I've got 230 volts coming through this side, and I've got 23 volts going that side. That is 10 times less than that. So if I've got 100 turns on my coil on this side, how many turns would I have on this side? So I've got 100 there, how many there? And remember, it's 10 times less on that side. So if I've got 100 on that side, I must have 10 turns on that side. And if I just use some different numbers, if I had 1,000 turns on this side, I should have 100 turns on that side, because this side is always 10 times less than that side. So if I had 500 turns on this side, I should have 50 turns on this side, because I've got 230 volts coming in, I've got 23 volts coming out and going into my laptop, because 230 is way too much for my laptop. It'll blow the laptop up, it'll heat the battery up, and the battery can explode, catch fire, and that will be bye-bye Mr. Meehan, because you know everything will be on fire. So that's what's happening inside a transformer, not a robot in disguise. So quick little thing here then. So little assessment here, quick. Could you put these in order of which way they should go? So pause the video and try to work out in which order do these steps go. Pardon the pun. Step up. No. Anyway. Okay, so have a go at that. Pause the video, write these out in the correct sequence. So which one goes first, put them in the right order, and then just do an arrow and match them up so you can put them to your notes. Pause the video, have a go at that. Once you're done, I'll go for the answers. So I'll just press solve, slow. Put them into the right order, there you go. So that is the power station, then you have your step up transformer, then you have your national grid, then you have your step down transformer, and then it goes to your homes and your factories. So now, if you'd notice, if I just go back a notch, if you notice I've got AC here. Okay, what does it mean by AC and DC? Now, there's two types of current. There's one called direct current and one called alternating current. DC stands for direct current. AC stands for alternating current. What's the difference? Well, DC means that the current will only keep going round and round one way around that circuit. It's a direct current. When you use batteries or cells, you only get a DC current, a direct current. So if I put my battery in this way, and let's say the current goes this way around, it'll always go around that way with that battery. However, if I put the battery the other way around, if I flip it around the other way, the current will go the opposite way round. That is known as a direct current, and you get that from cells and batteries. So here is my, this is a little screen that you'd find on something called an oscilloscope. An oscilloscope is just a box, it looks like an old-fashioned TV with a little screen on it about this size. Okay, about approximately about that size. And in there, on that screen, it looks like a piece of graph paper. And it's usually a green screen. And you have a little dot on that screen being fired. It's something called cathode ray oscilloscope, you don't need to know that. But it fires this little dot and it makes a line on that screen because that dot is moving along. And it's just basically a graph paper. And it's measuring the electrical energy, the voltage, the potential difference there. So if you imagine that's 0 on my graph paper there, that's the x-axis. And this is my y-axis, okay? Now imagine each box is worth 2 volts. That means that will be 2, 4, 6, 8. So I'll go up to 8 volts. Now this one will be -2, -4, -6, -8. What does it mean? It's just the direction. So if I have my battery that way around, it'd move that way. If I turn my battery around the other way around, the line will move that way. Is there a difference between the plus and the minus? No. They're exactly the same. They're exactly the same. All it is the plus means one direction, not the band, by the way. It means, let's say it's going that way, and if I turn the battery around, the minus just means the current's going the opposite way round. Okay, so that's all that means. So this will be then, if I had to read the screen, this will be 2, 4, and it's halfway between 4 and 6, so this must be reading 5 volts. If I had the same line, but on this side, it'll be -5 volts. If I keep adding extra cells, you'll see the line will just keep going up. So that's a direct current. You can see that it just stays at a particular voltage. There's no fluctuations. Okay. Now, what do I mean by an alternating current though? An AC current, alternating means it's changing directions every second. But depending on how often does it change direction? Well, why is it changing direction? Does a battery go back and forth? No, it doesn't, right? So, but this would happen if you had a battery and you, all of a sudden you kept spinning it back and forth, really quick. That's what you'd see. But that's not what's happening. What's happening here is what's coming out of the power station. Now, if you remember in the power station, we just need magnets and we need wires and we need movement. So if the magnet is spinning round, when the magnet is facing one way, you get current going one way. And when the north and south of the magnet is facing the opposite way around, the current moves the other way around. Now you will learn about this in more detail when we get into that topic in year 11. But ultimately that's why this is going up and down, like this. So the magnet is spinning round and round and round. And when the magnet's one way, the current goes one way, it's like in the positive direction. When the magnet's facing the opposite way, it goes to the other way. But again, there's no difference. It's just it's not the magnitude, because the magnitude is exactly the same. It's just the direction. So this is the positive, and this will be negative. So if this was going up in 2 seconds, that'd be 2, 4, 6. That'd be +6 volts there, and this will be 2, 4, 6, -6 volts there. Okay. The one last thing you need to know about this then is that, well, how many waves do I get going past a second? So if you imagine this time base here, I've got 2, 4, 6, 8, 9, usually I have 10, but let's just say there's 10 boxes across there. Let's say this is 1 second wide. So the time it takes to get from here to here is 1 second. This here is showing you how many waves are passing a point every second. So if this is the equivalent of 1 second, and this is 2 waves going past in 1 second, that would be 2 hertz. It's 2 waves per second. If I just had 1 wave going past this point in a second, it'd be 1 hertz. It's 1 wave per second, or 1 cycle per second. So the frequency is how many waves do you get going past every second. Now, the voltage at home then, which I'll come to in a second, is 230 volts. However, the frequency that comes through our sockets in the UK is 50 hertz. 50 hertz. So what does that mean? 50 hertz, 50 waves per second, 50 cycles per second. So you get 50 of these waves going past you every second. What does that mean in the power station? It means that magnet is spinning round 50 times in 1 second. So that's extremely quick. Now, a place where you might have seen this sort of thing in action is if you take a photo, get your mobile phone and watch TV, and you take a photo of your TV, you might sometimes get a weird effect where you've only got half a screen there and the other one's like blank up there and there's like half a person there or something. You might think, well, what's going on there? Another place you might see something strange is when somebody's being interviewed. It's like here, me standing in front of a camera. I might be being interviewed by a camera and I've got a TV going on in the background, or there might be some work on the PC on the background, or some TV show going on in the background. As being interviewed, you might notice you've got this flickering, weird flickering happening in the background on the screen. Well, why is that happening? Well, it's to do with frequency. The frequency you're watching me and the camera is filming me might be a different frequency or a different refresh rate to what the screen is doing. So they're out of sync. So what are you actually seeing on a TV screen? Well, if the TV screen is 50 Hertz, what you're actually seeing isn't moving pictures when you're looking at a TV, when you're watching a movie. What you're getting is 50 pictures coming to you every second, being broadcasted to you. So how does it look like they're moving? Well, if you imagine a flick book, if you imagine you draw those little stick people on the flip, you know what I mean by flip book, and it's like the little person is, you're drawing them, each page is a different little picture of a person kicking a ball, let's say, and as you flick that book, it looks like those little pictures are all stitched together. It makes it look like that the person is moving and kicking the ball. And that's exactly what's happening on your TV screen. You're getting 50 pictures per second. And if you take a snapshot of that, you might only get half of that picture. And that's to do with frequency. It's how often is it being refreshed. It's being spun round, 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 round. So I thought just a little bit of general knowledge there for you. Now, the last thing then, to finish this particular lesson on, the UK mains electricity then, in our country we have 230 volts of electricity, electrical energy coming through our sockets. However, your live wire, now I'm going to, on my next video, we're going to look at plugs. On that video, on that YouTube video, you'll see me stripping my Dyson wire, and you'll see that it's exposed. You'll see a live wire and a neutral wire. Now it's the live wire, the live socket, okay, what's coming through is the dangerous one. It's the one that's going to kill you. Now the live wire isn't actually 230 volts. The live wire, if we just connect it to the live wire, you'd actually get up to 325 volts. Okay, so you'd get this kind of cycle here. It goes actually above the 230. Okay, but the actual mains itself, the whole network is on 230 volts when it's connected. So when I put a plug in there, it's on 230 volts. But if I was just connected to the live wire, because that live wire is connected to my substation, that will be giving me 325 volts. Okay, because that live wire is not earthed yet. So that's the last bit of information. So if this has been useful, please like the video, share the video, and subscribe, that kind of jazz. Next lesson, we're going to go on to UK 3-pin plugs, the different components to them and how they're wired. So that's the end of today's lesson on mains electricity. I hope it's been useful. Take care, and I'll see you next time on My Smart Learning. So